A square matrix A with the same number of rows as columns is orthogonal if the transpose is the same as its inverse. So this implies that the transpose of A by A is equal to A by its transpose, and that's equal to the identity matrix. So given this example, if we transpose A, we obtain cosine theta unchanged on the diagonal, and sine theta gets swapped with minus sine theta. And if we invert the matrix, we get the reciprocal of the determinant of A, where the determinant of A is cosine squared theta minus sine squared theta, which gives 1 by the trig identity. So the inverse is 1 on 1, and we swap the cosine thetas, and negate the sine thetas. So these two matrices are the same. Now the row and column vectors of an orthogonal square matrix A form an orthonormal set in the real inner product space of R tuples with the Euclidean inner product. So for example, the first row vector of A has components cosine theta and minus sine theta, and the second row vector has components sine theta and cosine theta, and then taking the inner product, we have cosine theta by sine theta minus sine theta by cosine theta, which is 0. And you'll get the same result for the column vectors. So the row and column vectors of an orthogonal square matrix form an orthonormal set. Let's observe some properties of the inverse of an orthogonal matrix A. So as we've seen, if we take the inverse, we have the determinant of A is cosine squared theta minus sine squared theta, which by the trig identity gives 1. So the inverse is the reciprocal of the determinant, which is 1, multiplied by this 2 by 2 matrix, with the cosine thetas being swapped, and the entries off the diagonal are negated. So we can see this matrix is orthogonal because it's equal to the transpose of A. Now the product of orthogonal matrices is also orthogonal. So for example, if we take the product of A with itself, we get cosine squared theta minus sine squared theta, and minus sine theta cosine theta minus sine theta cosine theta is minus 2 sine theta cosine theta. And then we have sine theta cosine theta plus sine theta cosine theta, and minus sine squared theta plus cosine squared theta is cosine squared theta minus sine squared theta. So if we use some trig identities, the entries on a diagonal give cosine 2 theta, and the entries off the diagonal give minus sine 2 theta, sine 2 theta. So essentially multiplying the same rotation matrix with itself results in a rotation matrix that doubles the angle of rotation. And you can easily verify that this matrix is orthogonal by multiplying it by its transpose, which should give you the identity matrix. And furthermore, for an orthogonal matrix A, the determinant is either 1 or minus 1. So for example, if we swap the rows of A, we have sine theta and cosine theta in the first row, and cosine theta minus sine theta in the second row. And you can easily verify that this matrix is orthogonal, but the determinant in this case is minus sine squared theta minus cosine squared theta, which gives a determinant of minus 1. If L is an R by R square orthogonal matrix, then we consider the matrix L as an orthogonal linear operator. So here we have the linear operator on a vector V, and the norm of this product is equal to the norm of V. For all vectors V, in the real inner product space of R tuples, and a dot product between L by A and L by B results in a dot product between the two vectors. For all vectors A and B, in the real inner product space of R tuples. So the first property can be seen if we write the norm as a dot product with the resulting vector and itself to the 1/2. So that gives the square root of the squared norm. And therefore, we can write this dot product in matrix form as L by V transpose multiplied by L by V. And this becomes V transpose by L transpose by L by V to the 1/2. And for an orthogonal linear operator, this product evaluates to the identity matrix. So we have V transpose V to the 1/2, and this is the same as the dot product between V and itself to the 1/2, which is equal to the norm of V. And you can easily verify the second property by writing the dot product in matrix form as we did here. If we have an orthonormal basis O for an R-dimensional inner product space V, and if the coordinate vector A in V relative to the orthonormal basis O has the coordinates A1, A2 up to AR, and B is another coordinate vector with respect to the orthonormal basis, which has the coordinates B1 to BR. Then the norm of A is the square root of the sum of its components squared up to AR squared. And the distance property between the two vectors also holds. So that will be the square root of the sum of the difference between the components squared. So we have A2 minus B2 squared, and so on up to AR minus BR squared. And the inner product between A and B is the sum of the products of the components of both vectors up to AR BR. Suppose V is a finite dimensional inner product space. So if T is the transition matrix from one orthonormal basis, which we'll call OA for V, to another orthonormal basis for V, then T is an orthogonal matrix. So for example, if we obtain an orthonormal basis by rotating the xy axis by an angle theta in 2 space, then every point in 2 space, so for example point P, will have coordinates relative to the old basis. So these would be x and y, and also relative to the new basis, which will be x dash, y dash. So if we take our unit vectors for the old basis as I hat and j hat, and for the new basis there'd be I hat dash and j hat dash, then we can write the unit vector I hat dash as cosine theta in the direction of I plus sine theta in the direction of j. And similarly j hat dash, given that this angle is also theta, can be written as minus sine theta in the direction of I plus cosine theta in the direction of j. So the transition matrix from the new basis to the old basis has entries of cosine theta, sine theta, minus sine theta, and cosine theta. So essentially, the transition matrix from the new basis to the old basis is orthogonal, and if you take the inverse of this matrix, that'll be the same as its transpose, which will give you the transition matrix from B to B dash, which will also be orthogonal.